Is everybody getting the synthetic division part? Finding a root and factoring it out? You want to factor till you get down to the square. Because once you get to a square, you have multiple ways to factor that. Factoring, quadratic formula, complete the square.
And behavior is just like calculus.
The end behavior is when I'm cubed and cubing, the ends are going different ways. When I'm positive, the left goes down, the right goes up. End behavior. Today we're going to do more with asymptotes, and that helps us also define end behavior. But these guys on the cubing, when it's even, they either both go up or down. So if it's positive up, negative down. Just so that you get used to describing it. So when you get to here, you should be able to see, like in your head, what it's pretty much going to look like.
Did you put decreasing like 027?
Decreasing from here to here. What's this x value? Should be 5. Catch all my mistakes, but I don't know what. Like I said, I had to redo all these, so I just copied them. So for my copying, I kind of messed them all up probably. Good? Okay, and last one. So now I have 4 roots. 4 roots, 3 terms, 2 inflections. And it's an even, so my end behavior is going up. Both ends go up. So usually that kind of tells me either I have something with like, almost looks like a weird U or a W I get out of this. And this is going to give you a W. And did this have imaginaries? No. It didn't. So somewhere this is a little bit off. You had a double root. And how did I know this was a double? This is bouncing off the 2. It's probably just same thing with my, I can't get any closer to this. Bouncing off the 2. You can kind of see it when you graph it. So that's a double. So if you want to divide it back out again. Otherwise you're not going to find another root because the other one is a irrational one. Make sure you also state absolutes versus relatives. You guys are pretty good about the absolutes and the relatives. I'll copy that while I just scan this out. A restriction in your denominator that says can't use this certain number. We have asymptotes. We also have point of discontinuities in here. So remember what I was telling you about when you had to describe, when you remember when you did that lab with the little bubble thing? And there was 2 asymptotes there. And one you could just about see you got from the x, and the other one you could just about see was a y equals something. And I said, we'll talk about those. This is where we do the asymptotes. So once you kind of understand asymptotes, it's going to make life a little bit easier. Again, your x and your y intercepts. Your y intercept is when x is equal to 0. You're going to solve for y. Your x intercept, we're going to do this a little bit differently. Your x intercept is when y equals 0. We're going to find your zeros of your numerators. So we're going to work on this in a little bit. You're going to get 2 sets of asymptotes, possibly. A vertical asymptote, which after we factor and reduce, it's whatever's left on the bottom in the denominator. That's going to be an asymptote. Whatever we factored out is later going to be a point of discontinuity, a little further down. We still do our domain and range and find out all the values we can't use. A vertical asymptote, your graph will never ever cross your vertical asymptote. But, put a little asterisk over here. This is what determines your end behavior. This one and this one. I want you to put little asterisks here. This is how you get your end behavior. for both of these guys. An asymptote, it says I can't use this, but I'm going to help you guide your graph with this. You're going to get closer and closer, but never touch. Now, a vertical asymptote, your graph will never ever cross. That comes from your denominator. Those are values of x you cannot use. A horizontal asymptote, you can cross, because a horizontal asymptote is end behavior only. It just helps you guide your graph. So if your graph jumped over it, it would still come back down and use that as a guideline. So we'll see cases of this too. But a vertical, we will never cross a vertical. Just so that we can kind of do some of these together. Domain and range, max and mins, increasing, decreasing, concavities, you saw all these. Now, sometimes with these, we don't get max and mins. So if your graph is going like this, and getting closer and closer to that asymptote, there is no max and min on this. Because your max is as high as it can go, your min is as low as it can go. There's no relatives in here. Because this is getting closer and closer up here, closer and closer down here. So some graphs will not have max and min. They will have increasing, decreasing, and this also will give you a concavity. Because even though it doesn't go all the way around, it's still making a cave down motion. It's a little bit weird. That was one thing that I always had a hard time with, like, that seriously is not a cave. But it gives you a concave down motion. A pointed discontinuity, we'll talk about that tomorrow, not today. But when we factor and reduce, whatever we can reduce out of your denominator is going to be a little point that your graph can't use. And this is a concept of calculus that we talk about again at the end of this year, and the first thing you talk about next year in calculus. A slant asymptote, we'll talk about this tomorrow also. Is an asymptote, sometimes your graph goes like this. What made this do that? Well, there was a slant asymptote here that made your graph go like this. Because again, asymptotes guide your end behaviors. So these two things we're going to save for tomorrow. Today we're just going to give you like basic. This is not much different from, remember when we did the rational inequalities? You had like, I'll just say x minus 2 squared. And we set this greater than or equal to 0, and kind of found the different parts of it there. It's not much different. It kind of works the same because there are rationals. Rational meaning something's going on. It's not a continuous. You're not putting your finger down and never taking it up. You have to put your finger down, jump over something. And those are the things that we'll look at in here. So keep that handy, because that's kind of a nice thing to just keep with you so that you can see what we're doing. Oops, it was underneath it. So if you kindly throw this in your calculator, and let's take a look at this. We're going to sketch and describe this completely, using your chart, using your domain and range. Don't find domain and range right off the bat, because we have to find your restrictions first. So if you sketch this. Just give me a little sketch. Side is always off, and not this side, but always that side. So you see your graph going here somewhere, and you see your graph going here somewhere, right? Is that what it looks like so far? Okay, so from left to right, as I came through the left, something said, whoops, you can't cross this barrier. And then this will go on and on and on and on and on forever. And then I come back up here where it restarted and said, whoops, you can't cross this barrier. And I restarted and went here. Something else said, whoa, there's a little gap right there, right there. I can't use it either. So I'm going to have to figure out what those are. So the first thing we're going to do is domain. Are there any restrictions here? X can't be 0. So we're going to take it out of our domain. Right. Range, I'm not sure of the range yet, because I don't know what's causing me to stop there, go up there. I can see I can use all the ones going below, all the ones going up, but there's something in the middle that I wasn't able to use. So we don't know that yet. Okay, so now, follow your sheet. We're gonna try to walk through this together. Your y-intercept. This is when x is equal to 0. Just plug a 0 in here. Do we have a y-intercept? No, because we can't divide by 0. So you're just going to have to show that to me. If we were able to factor this and reduce this, we would. But right now, today, we have no slants, we have no points of discontinuity, so nothing can be factored out of that. An x-intercept. This is when my y is equal to 0. But we have a little special condition here. We say, instead of finding it this way, because it can't do it like this, we say just set your numerator equal to 0. A little different. Just take the numerator, and that's after we factor, but we can't factor, because we wouldn't be able to do this. If we could cross multiply, you'd get the same thing. So we're setting our numerator equal to 0. Subtract 1, divide by 4. So does it kind of look like it's crossing by the negative 1/4, 0? We're close enough there, right? So we know we have no y-intercept, and we have one x-intercept. This is going to be our little shortcut. Set your numerators equal to 0 after we factor, but I couldn't factor anything. So let's find your vertical asymptote. Something is causing me to bounce off of this thing right here. A vertical asymptote. A vertical asymptote says after factoring and reducing our factors down, which we couldn't do that, take the zeros of the denominator. And it's not all my domain restrictions, it's whatever's left after we factor. So in this case, x is equal to 0. Vertical asymptote, VA. Sorry, my abbreviation. Vertical asymptote. Just use VA, HA, SA. So where is the line x equals 0? The y-axis, right here. Isn't that my x equals 0? And did I never cross that? Something in my denominator can never cross that. Okay? Now, horizontal asymptote has 3 things here. 3 things. You're looking to find your end behavior. You're looking at the degree of the numerator compared to the degree of the denominator. So the highest degree here is a 1. The highest is a 1 here. Just follow your chart for 1 minute. If you come down to it says the degree of the numerator, which is 1, is equal to the degree of the denominator, which is 1, then you're going to make a ratio. You're going to take these coefficients, and you're going to set it equal to y. When they're equal, we take their coefficients. If the numerator is less than the denominator, then we automatically use your x-axis, the y equals 0. If the numerator is greater than the denominator, we don't have a horizontal asymptote at all. But today, this one is the same as this one, so we make a ratio, a over b. This is a, this is b, technically. And our equation of a line is y equals 4, which kind of makes sense, right? What's happening right here? It's saying, don't cross over that line. That's an asymptote. I'm going to guide the end behavior for that one. Now, once you find your asymptotes and whatever point of discontinuities you might have, we can work on the range. So I'm going to come up here and do the range. So the range, I'm coming from my y's. I'm coming up from my y's, negative infinity. Whoops, what y can't I use? 4, so I jump over it, and I go up. So from negative infinity to 4, and 4 to infinity. Sometimes you kind of have to jump around a little bit. That's why domain and range are pretty far down on the list. Your max and mins, in this case, you have no max, you have no min. It's a continuous line and it's guided by your asymptotes, so there's no max, no min. Inflection point, no inflection points. What else is here? Increasing, decreasing, we can do increasing, decreasing. Increasing and decreasing. I'm reading from left to right. So what is my x value doing, what is my y value doing as I go from here to here? Decreasing. So from negative infinity to where? 0. And I can't touch the 0. Good. Then I go here. As my x reads from left to right, what is my y doing? Decreasing from where to where? 0 to infinity. That's it. Okay, and then we got to just do our concavity.
So now we write here.
You just have none. There's none. A lot of times when you see these and they're broken up, they're both going to probably be increasing, they're both going to probably be decreasing when they look this smoothly. And then concavity. Remember, concave up, concave down. This makes an upward one, even though it flattens out here, we still have kind of a cave going on in here. So this is a kind of a cave up. So from 0 to infinity. And this is our concave down from negative infinity to 0. Kind of the closest we can get to a cave there. Okay? Now I know we didn't get to this next one yet, but let's just see if there's anything weird here. Let's just hit the asymptotes for this guy. There's nothing we can reduce. Let me just hit the asymptotes with you, because that's the one that's going to be different. If I factor this, this is where my domain comes from. My domain says, can't use 1, can't use negative 1. My range we can worry about later. Now, these guys are also going to be my vertical asymptotes. They're in my denominator. So there's 2 asymptotes I have there. Now my horizontal asymptote says this. Take the degree in the numerator and the degree in the denominator. If the degree in the numerator is less than the degree in the denominator, then my asymptote is my x-axis. My y equals 0. If the degree in the numerator, it's on your sheet. I think it's the top one. If the degree in the numerator, 1, is less than the degree in the denominator, 2, then I have a y equals 0. You're only going to get 2 of them if you think about it. A y equals 0 when that happens, and when they're equal, a ratio. If one's greater than the other, no.
So how come for the first one you use 4 and 1?
Because both of them had, this is what you're looking at, the degree. The first one, they had 1 and 1. The degrees were the same. So x to the 1, x to the 1. So we took the coefficients of their x's. Now, in this guy, just hang with me 1 second, guys. Your graph is going to go like this. Start with your asymptotes. My asymptotes, when you graph this, the rest of it's going to look the same. But this guy's going to cross over here. He's allowed to cross because the object is and behavior. This one's going to go down here. This can never cross a vertical, remember. a vertical guy here. A horizontal, yes, but not vertical. And this guy is going to go like this. The rest works basically the same. So the asymptotes are the ones I wanted to hit. Remember, zeros are zeros of your numerator. Try the homework and see how far you get. Keep this next to you. You need to see the sheet with you.